Okay, welcome to this next part of advanced separation topics on distillation. I hope by now you have got enough background, revised enough about uh, the undergraduate topics of distillation, such as McApthil. You have also revised concepts about uh, thermodynamic concepts like thermodynamic models, which models should we use, how do we apply them, the bubble point temperature, knowing pressure and liquid phase composition. How do you find the temperature and the vapor phase composition? So what we call as a bubble point temperature or dew point temperature, knowing the vapor composition and the pressure. How do you find the temperature and the liquid phase composition in equilibrium? So all those concepts are important. What we are going to look at now is something called as residue curve maps. So we will talk about what these residue curve maps are and how they can be generated. So what is a residue curve map? That is the first point. Second point is how do you get one, or how do you generate a residue curve map? And third thing that we are going to talk about is what is the use. Okay, so we are going to talk about all these 3 points one by one, but let's start with what is a residue curve map. For that, what we are going to look at is a concept that you have already seen, uh, that is from a batch distillation. So recall what you do in a batch distillation, that you have a distillation flask. Let's say we have a binary mixture of A and B in this flask. A is more volatile and B is less volatile, and then the mole fractions of the liquid in the liquid phase we call as XA and XB. Now we heat this flask, the vapors that are generated, so these vapors, let's we call these compositions in terms of a symbol Y. So Ya and Yb are the mole fractions of A and B in the vapor phase, and what we say in a batch distillation is these Ya and Yb are in equilibrium with Xa and Xb, in thermodynamic equilibrium, right? So how do you describe the thermodynamic equilibrium? That P into Ya is gamma A, Xa and Pa sat, right? You must be recalling this from your thermodynamics lectures. So P total pressure into Yb would be gamma B Xb into Pb sat. Now when we condense these vapors, so we send these vapors, or these vapors go through this condenser where they get cooled and they get condensed, and we collect them in a distillate or a receiving flask, or we call it as a distillate. So this distillation flask we call as residue, or simply bottoms, or we call it as a still. So many different words we use interchangeably. So be aware of all of these concepts, recall all these concepts. Okay, so when we uh, um, when we distill out something from this bottom mixture or a still, the more volatile component is going to get enriched in the vapor. And that it's more volatile, that's how it gets enriched in the vapor, and that's how we do the distillation. And that's how in successively in a continuous rectification or continuous distillation column, we enrich the more volatile component at the top, and we get a enriched less volatile component at the bottom. Now we let's recall that how we relate these compositions and quantities that are there. Okay, it's a simple distillation. You might have already done something called as experiment called as differential distillation. It is nothing but you relate the compositions and the mole fractions and the quantity that remains in the still. So first point is that if I try to write a material balance, so this is our material balance on this single stage, and let's say we say that Na moles are we say that, let's say, Na moles of A are vaporized. Na is the moles of A. So we can recall that these many moles of A, if they are vaporized, they must be coming from the total N moles that are vaporized. So we are saying that N or Dn, we are writing it in a differential sense, Dn moles are vaporized, and they are coming from this. So the loss of moles from this batch still, or from this kettle if you like, is Dn moles, right? And let's say Na moles or DNA moles, in a differential sense, DNA moles of the vapor have left this liquid. We are writing a material balance for this liquid. Our control volume is this liquid. So when we write this DNA minus DNA, the loss of the liquid must be equal to the Y, the mole fraction of the component A in the vapor. We don't have to write now Ya and Yb, it's a binary. So we'll just say Y as the Ya. Y is the mole fraction of the more volatile component in the vapor phase. So Y multiplied by Dn, and then this loss of the moles of A that has taken place from this batch liquid, batch still the liquid phase, we can write it as X multiplied by the total moles that are there in the liquid phase. So the total moles that are there in the liquid phase is, say, N, and X is the mole fraction of the more volatile component, that is component A. So derivative of X into A would be Y into minus Dn. So if you recall, this Dn is now actually minus Dn because it is a loss. We are writing a balance for this liquid phase. Okay, so now if you rearrange, what you will get is your Rayleigh's equation. This we call as Rayleigh equation. Do you recall that? And it is valid when I am vaporizing only a small fraction of the moles from the liquid phase. So suppose there are 100 moles of the mixture in the still, we are vaporizing maybe, let's say, 1 or 2 or 5. It's a very small fraction, and therefore the X and Y, they do not change, or X does not change significantly, and therefore correspondingly Y does not change significantly. But when I do over a period of time, how the liquid phase composition will change? The liquid phase will get depleted in more and more volatile component. So the X, that is XA in this particular case, will reduce with time. Correspondingly, at any instant of time, the mole fraction of more volatile component in the vapor phase Y would be related to each other by equilibrium. So these two at any instant of time are at equilibrium. That is the concept of batch distillation. And how are they related? If you could draw in terms of X versus Y, you could have a graph something like this, that at any particular X, what is the value of Y. Okay, and as X depletes in the liquid phase, so Y also depletes in the vapor phase. When we say depletes, what I mean is the X reduces with time because the more volatile component is getting stripped out of the still. The amount of more volatile component left in the still reduces with time. And this equation we have used, we call as Rayleigh equation. And what you have done is you have done an actual experiment, which is our differential distillation experiment. Is you carry out this over a period of time, and you can relate what remains in the liquid and what is appearing in the distillate. So the from a differential form of this Rayleigh equation, now we are going to go to a integral form. Or if I say that I had Ni moles initially in the still, and we are finally distilling out some moles, and finally we are left with Nf moles, and the initial mole fraction of the more volatile component in the liquid phase was Xi, and the final mole fraction of the more volatile component in the liquid phase is XF, then using this differential equation, using this Rayleigh equation, we can now we can now do the integral form, and we can relate one with the other. So what I would need to do is I would need to plot a graph of x versus 1 over y minus x. So this is 1 over y minus x, that is the right hand side, and we integrate this from xf and xi. We integrate xf is reducing, so x is going towards left. We start with this initial xi and it is going towards this xf, right? So if we find the area under this curve, this area under the curve would be this integral of dn by n, which I can now say log nf by ni would be integral xi to xf dx over y minus x. So this is now our um, this is our integral form of Rayleigh's equation, if you like, right? So I want you to recall all these concepts, and what we would need to do is we would need to think about how we are going to do this calculation. And you remember, one most important thing that we have to remember is this y and x are related to each other. They are related to each other. Okay, so this y and x are related to each other. How are they related? They are related by equilibrium. So y and x are in thermodynamic equilibrium. If we were an undergraduate student, what we would have said, y is alpha x divided by 1 plus alpha minus 1 x. But remember, this alpha is not constant. It changes very, very dramatically. For example, if you see here, this y and x change very, very dramatically. The relative volatility here, relative volatility here, relative volatility here is very, very different. So take care that this is not a constant number. Alpha is not a constant number. They are related by um, thermodynamics. Okay, so you could use this in two ways. One way is like what you have done in your undergraduate experiment, distillation or differential distillation experiment. You vaporize some moles and you experimentally measure what is left here, and you try to integrate this, and then you know your thermodynamics. You say alpha is equal to 1.5 or 2, and then you say, oh, 1 is, you verify your Rayleigh equation. That's the experiment you have done in your undergraduate course. But now we are going to use it in a slightly different way. One of the ways we can use is, if I vaporize a small quantity, I can always find how this curve should be, what should be the shape of this curve, whether this shape should be like this, whether this shape should be like this, whether this shape should be like this. We can find out something about this curve in the sense that we can find out how y and x are related to each other over this small change. If I do a small change, so let's say, for example, if I start with 100 moles in the mixture and I vaporize say 10 moles, I can find out how this, I can do a measurement and find out what is the value of xi that I started with and what is the value of xf that I ended up with. So the left hand side we would know, correspondingly xi and xf we would measure. Now we could back calculate what should be the value of alpha over this range of xi to xf. And now I can do this repeatedly. So start with 100, distill out 10 moles, find xi xf. Now start with the remaining 90, distill out 10, find out what is the xi xf. We can find out alpha as a function of x. So you can use it to determine the relative volatility, and how this relative volatility changes, and then you can fit your thermodynamic model to this. you have in a sense found out what is the value of y over this range of composition xi to xf, provided we are, of course, we are alpha changes very dramatically, therefore we are not going to find alpha over a wide range. Let's say from mole fraction 0.9 to 0.2, we will find from say 0.9 to 0.8 when this xi changes from 0.9 to 0.8, then 0.8 to 0.7, 0.7 to 0.6, 0.6 to 0.5, and so on, and we'll find alpha over this range. So that's how we could do an experiment to find more about how the x and y are related to each other, or we can in a sense fit some kind of thermodynamic model to our data of x and y, and then we can use it for whatever purpose we would like. Another way we are going to do is, if I keep on distilling uh, material from the still, so we start with 100, let's say we distill out 10, we find out what the xf is. What we can do is we can generate a curve of, we start with 100 moles, so let's say this is our n and this is our x, so this is our xi initially, let's say xi is say 0.9, if you like, whatever value you want, and let's say we start with 100 moles. 100 moles. Now we distill out 10 moles, we find out what the remaining x is. We distill out 10 more moles, we find out what the remaining x is. We distill out 10 more moles, find out what the relative, find out then what the value of x is. So we could generate how the composition, we can find out how the composition of the residue changes as we distill out more and more material. So how, or what we mean is how the residue composition changes. That's why this is called as a residue curve map, how the residue composition changes. So we call that as a residue curve map. We'll see more about this, how to generate this residue curve map now. Okay, so we are going to use this Rayleigh equation now to uh, to generate what we call as a residue curve map. So be very, if you want, you can stop this lecture, go back to your concept, solve one or two problems from your undergraduate course on Rayleigh equation, so that you are clear what we mean and how we are going to use this Rayleigh equation. Now let's start with this Rayleigh equation once again. What we are going to do is we are going to write this Rayleigh equation little differently. We are going to say zeta or d zeta is a fraction vaporized, so that's nothing but dn by n. Remember, if we start with 100 moles, we are vaporizing, let's say 10 moles, so dn by n is 10 by 100, so 0.1, and minus sign is there just because we are vaporizing that. So if I use these two equations, then I could say, I could rearrange this Rayleigh equation into a more usable form. Dx by d zeta is x minus y, and remember this y is in equilibrium with x. Y and x are in thermodynamic equilibrium. So if I know how x and y are related by thermodynamics, either in terms of relative volatility or in terms of some thermodynamic model like NRTL, like Van Laar, we could use this d zeta or zeta as a parameter and find out how the x would change as I keep on distilling out more and more material. So this equation is what we are going to use to generate what we call as a residue curve map. Right, so let's talk about this a little bit more. What exactly are we going to do? Remember, this is a first order differential equation, and this first order differential equation, so you remember what your first order differential equations are. You could solve them using Euler's method or Runge-Kutta method, whichever one is your favorite. But let's just say simplified, we were going to use Euler's method, and it's a good method provided your d zeta is very small. So we can integrate this. How we are integrating this? So dx by d zeta we will say is delta x by delta zeta is equal to x minus y, or if you would like, we could say this as x new minus x old would be equal to delta zeta multiplied by x minus y. Recall Euler's method. So what you had done in your Euler's method, dy by dx, if you wanted to solve as a function which was a function of x and y, what you said is yi plus 1 next time step or next step of x is equal to yi plus delta x multiplied by function x I y I, function value to be evaluated at the previous step or at the previous value of x, right? So what are we going to do is we are going to generate this, use this equation, first order differential equation, to generate the residue curve map. Okay, let's try to think about how to generate this residue curve map. So if I start with, let's say, a binary mixture, so first of all let us write it for a binary system, right? So binary system is going to contain A and B. So suppose I start with, in my still, so remember this is our distillation still, we start with this still, I'm just taking some example. We start in this still, suppose XA is equal to 0.8 and XB therefore is 1 minus XA, which is 0.2. Now I have to take what is the equation that we are solving? We are solving dx by d zeta is equal to x minus y. So first of all, I have to find out what this y is in corresponding in equilibrium with this particular x. So how will we do that? I have to find a bubble point temperature. So what we will say, Pya is equal to gamma A XA PS at, Pyb is equal to gamma B XB PB sat, and then if you add, you will get the total pressure equal to gamma A XA PA sat plus gamma B XB PB sat. Okay, so I will have to first of all to find what is y in equilibrium with this particular x. With this particular x, what I will need to do is, first of all, I will need to guess my temperature. So guess my temperature. We will guess this. We will calculate the corresponding value of PA sat. We will calculate the corresponding value of PB sat from this guessed temperature. Then we will calculate gamma A corresponding to the temperature. The thermodynamic parameter would be dependent on temperature, maybe Margulies equation, maybe Van Laar. Those constants are dependent on temperature, and gamma A would depend on XA and XB, and correspondingly gamma B also we will calculate. And then we will calculate the total pressure from this equation. Now we'll check if, so we are going to do this distillation at 1 atmosphere pressure, let's say. So we'll check whether this pressure that has been calculated from this equation is 1 atmosphere or not. Otherwise we will vary this guess temperature, right? So you can use a goal-seek function in Excel. Goal-seek the value of pressure to be 1 atmosphere by varying this temperature. Now once you get this pressure to be equal to 1 atmosphere, now we can calculate Ya and Yb. So if I just put some equation, let's say equation number 1, equation number 2, equation number 3. So pressure we are going to calculate from equation number 3. Ya we are going to calculate from equation number 1. Yb we are going to calculate from equation number 2. Okay. If you want, you can stop this video anytime and think about what we are doing. Let me just write it little on lower side because the camera is sort of hiding that. what we did was we started with, let's say, XA equal to 0.8, XB equal to 0.2. We guessed temperature. We calculated PA-SAT from Antoine equation, PB-SAT from Antoine equation. We calculated total pressure from equation 3, and we varied our guess temperature to get the total pressure to be 1 atmosphere, because we are doing distillation at 1 atmosphere. If we were doing a distillation at 0.5 atmosphere, we would have varied this guess temperature to get total pressure to be 0.5 atmosphere. Then we calculate YA from equation 1, and we calculate YB from equation 2. Okay, so now this YA and YB that we have calculated are in equilibrium with this XA and XB. Right, do you recall? Now, so we have not done the distillation yet. We have not um, uh, we have um, uh, we have not yet distilled out anything. So our zeta, the fraction that has vaporized, is 0. That is our initial condition. So this is our initial condition. Now if we say, suppose our delta zeta is 0.1, so that means now the new value of zeta is 0.1. What will I do? X new would be X old plus delta zeta multiplied by X minus Y. Y is in equilibrium with the X at the previous value of zeta. Right? So now this value XA, what would that be? This value would be 0.8 plus delta zeta. What is delta zeta? 0.1 X at the previous value of zeta. What is it? 0.8 minus this value of YA. Okay, that would be the new value of X. And of course, XB would be 1 minus XA. So we don't have to solve it for XB. It's a binary. If it was a ternary, we would have had to solve for two components. Component 1, component 2. Component 3 would be 1 minus X of 1 and X of 2. Like this, we are going to do marching in zeta. So zeta would be 0.2, zeta would be 0.3. Every time you take a step, you complete this, and you will be able to get how the XA would change. Now suppose, just talk about the binary. So suppose we are having our binary system A and B. So A is our more volatile component, so we say A, XA is equal to 1 here, XA is equal to 0 here. This means XA is equal to 1 means pure A, XA is equal to 0 means pure B. So how would our residue composition change? If we start with this residue, if we start with, let's say, if we start here 0.8, so suppose this value is 0.8, this value is going to go lower and lower, because I am going to distill out more and more of the more volatile component. What is going to be left in the still is going to be richer and richer in B. Okay. So do you agree? Suppose I start with 0.5, it is going to become after some time 0.4, 0.3, 0.2, 0.1. Right? The residue remaining in the still is going to be more and more depleted with respect to the more volatile component. That's our residue curve. So for a binary system, this is how our residue curve is going to look like. Now, suppose we talk about the minimum boiling azeotrope. What do you mean by minimum boiling azeotrope? So if we have A and B, this is our minimum boiling azeotrope. So minimum boiling azeotrope. So this is pure B, sorry, this is pure A, this is pure B. XA is equal to 0 here, XA is equal to XA is equal to 1 here. Suppose our azeotrope composition is, let's say, XA is equal to 0.7. Recall when we talked about this, our txy curve was looking like this. So suppose this was 0.7 t x and y. This was the tx curve, this was the ty curve. Okay. So suppose when we distilled out, suppose if I am starting on the lower side of this azeotrope point, say I'm starting here now in my distillation flask here. What is more volatile? The azeotrope is more volatile. So what would be distilled out would be more and more of the azeotrope. What will remain in the still is going to be the less volatile component, pure B here. So this was pure B, this is pure A. So the residue composition is going to shift towards the less volatile component. If I start on the right side of the azeotrope, let's say I start with Xa equal to 0.9, again because it's a minimum boiling azeotrope, the azeotrope is more volatile, that is going to get distilled out more. What I'm going to be enriched in the still is going to be pure A. So the residue is going to curve, or residue composition is going to shift towards the right. So this is how the residue curve map would look like for a minimum boiling azeotrope. Now if you think about a maximum boiling azeotrope, how would that look like? The maximum boiling azeotrope looks something like this. Let's say so this was our Tx and this is our Ty. This is pure B, this is pure A, and this is the maximum boiling azeotrope. Suppose the azeotrope composition is, let's say 0.4, just some value I'm taking just so that we can illustrate. So now if I want to depict it on a binary, this is our Xa equal to 0, our Xa is equal to 1 here, this is our 0.4, the binary azeotrope. It's a maximum boiling azeotrope. Now if I start on the left side of the azeotrope, what is more volatile is the pure B. So the pure B is going to get enriched into the vapor phase. The liquid phase, what is remaining in the still, is going to contain more and more of this azeotrope, right? So the residue curves on the left side, if I'm starting on the left side, they are all going to point towards the to the azeotrope. If I start on the right side of the azeotrope, now the more volatile is pure A, the less volatile is the azeotrope. So as I distill out more and more, the residue is going to contain more and more, closer and closer to the azeotrope. So the residue curves will point towards this. Okay, but you can actually calculate this. What I would like you to do, not just for binary now, what we would like to do is do this for a ternary. That's more important, that we do it for a ternary system, and we depict this ternary on a triangular diagram. So what I would like you to do is generate the residue curve map for benzene, toluene, xylene using Raoult's law, or methanol, ethanol, propanol using NRTL, acetone, methanol, water using NRTL, acetone, chloroform, benzene using NRTL. And all these NRTL parameters are there. You can refer to some papers or you can refer to some books. You will easily get these NRTL parameters. I want you to generate these residue curve maps for let's say benzene, toluene, xylene at 1 atmospheric pressure. What I would like to do is I will show you one case for benzene, toluene, xylene, and I will then request you to do this other three as with using NRTL model as homework. Okay. Okay, so if you want, you want pause the video, you can make sure that you understood so far right now how the residue curves look like for a binary, and then continue to this ternary system now.